Hello everyone and welcome to this video on number system. In this video we will discuss the divisibility rule of certain numbers. We will also understand the remainder theorem. So let us first start with the divisibility rule. Suppose if you want to determine whether a number is divisible by any number which is of the form of 2 raised to n, or if you want to find the remainder when any number is divisible by a number which is of the form of 2 raised to n. So how we will do that? Let us consider an example 1, 2, 3, 5, 9, 2. If you want to check whether this number is divisible by any of the number 2, 4, 8, 16, 32, or if you want to find the remainder when this number is divided by any number of the form 2 raised to n. So all you will have to do is check whether the last n digits are divisible by the respective number or not. So what is the value of n? In case of 2 is of the form of 2 raised to 1. So the value of n is 1. In case of 4, which is of the form of 2 square, the value of n is 2. In case of 8, which is 2 cube, the value of n is 3, and so on. So if you want to check whether this number is divisible by 2 or not, you will have to check the last one digit. In this case, the last digit is 2. Since the last digit is 2, which is even, which is divisible by 2, we can say that this number is divisible by 2. Likewise, for 4, if you want to check whether this number is divisible by 4 or not, we will have to check the last 2 digits. So in this case, the last 2 digits are 92. Since 92 is divisible by 4, we can say that this entire number is divisible by 4. Similarly, if you want to check whether this number is divisible by 8, since 8 is of the form 2 cube, you will have to check the last 3 digits. In this case, the last 3 digits are 592. 592 when divided by 8, as you can see, 592 is clearly divisible by 8. So we can say that this entire number is divisible by 8. In case of 16, which is of the form of 2 raised to 4, the value of n is 4. So you will have to check the last 4 digits. So the last 4 digits in this case is 3592. If you divide this thing by 16, we'll get 16 ones are 2s are, then we have 3, again 2s are, we have 6 carry over, 16 3s are. We'll have a remainder of 14. Since the last 4 digits are not divisible by 16, we can say that this number is not divisible by 16. So what is the remainder? The remainder will be 14. So by this method, you can check whether a number is divisible by any number which is of the form of 2 raised to n or not, and at the same time you can also find the remainder if the number is not divisible by that number. Let us consider another example 2, 5, 9, 6, 9, 3. So if you want to check whether this number is divisible by 2, 4, 8, 16 or not, or if not, then what is the remainder? So for divisibility by 2, we will have to check the last digit since it is of the form of 2 raised to 1. So since the last digit is 3, which is an odd number and it is not divisible by 2, we can say that this number is not divisible by, this entire number is not divisible by 2. In fact, since this is an odd number, it will not be divisible by any of these numbers. Okay, so in that case, we will have to find what is the remainder. So for that, in case of 2, we have to consider the last digit and find its remainder, which will be 1. So the remainder when this entire number is divided by 2 will be 1. The remainder when this number is divided by 4 will be given by the remainder when the last 2 digits are divided by 4. So in this case, the last 2 digits are 93. 93 when divided by 4, the remainder is 1. So the remainder when this entire number is divided by 4 will be 1. The remainder when this number is divided by 8 will be given by the remainder of last 3 digits when they are divided by 8. So the last 3 digits are 693. When we divide this thing by 8, 8 ones are, 8 8s are 64. We have a 5 carry, 8 6 is 48. So the remainder in this case will be 5. So the remainder of this entire number when it is divided by 8 will be equal to 5. In the same way, you can check for 16 by considering the last 4 digits. In case of 32, by considering the last 5 digits, and so on. Likewise, if you want to check whether a number is divisible by a number which is of the form of 5 raised to n or not, and if not, then what is the remainder? you will have to follow the same procedure as we have discussed in the case of number which are of the form of 2 raised to n. Let us consider an example and understand this concept. Let us take the number 1, 2, 4, 5, 7, 5. So if you want to check whether this number is divisible by 5 or not, 5 is of the form of 5 raised to n. So we'll have to check the last digit. Last digit in this case is 5, which is divisible by 5. Hence we can say that this entire number is divisible by 5. So if you want to check whether this number is divisible by 25, which is 5 square, you'll have to take the last 2 digits. So the last 2 digits in this case are 75. 75 is clearly divisible by 25. So we can say that this entire number is divisible by 25. Similarly, if you want to check whether this number is divisible by 125, 125 is of the form of 5 cube. So we'll take the last 3 digits. Last 3 digits in this case are 575. Now 575 when divided by 25, you can see that this number is not divisible by 125. We are getting a remainder of 75. So we can say that this entire number is not divisible by 125. So what is the remainder? The remainder in this case will be 75, which we have obtained by dividing the last 3 digits. Likewise, you can proceed for 625, which is of the form of 5 raised to 4, by considering the last 4 digits, and so on and so forth. Let us now understand the divisibility rule for 3 and 9. So if you want to check whether a number is divisible by 3, or if you want to find what is the remainder when that number is divided by 3, you will have to take the digital sum and check for divisibility. If we consider this number 39672, so we'll take the digital sum. So what will be the digital sum? It will be 3 plus 9, which is 12, plus 16 plus 6, which will be 18, 18 plus 7, 25 plus 2, which will come out to be 27. So 27 is the digital sum. So now since the digital sum is divisible by 3, we can say that this entire number is divisible by 3. The similar concept is applicable for 9 as well. Since the digital sum, which is 27, is divisible by 9, we can say that this number is divisible by 9 as well. Let us take another example. 1, 2, 4, 5, 7, 5. We'll find the digital sum, which will come out to be 3 plus 4, 7, 12, 12, 19, 24. So the digital sum is coming out to be 24. Now 24 is divisible by 3. Hence we can say that this entire number is divisible by 3. But 24 is not divisible by 9. Hence we can say that this number is not divisible by 9. So what is the remainder when this number is divided by 9? We'll find the remainder when the digital sum is divided by 9. It will be the same. So 24 by 9, the remainder will be 5. So the remainder when this entire number is divided by 9 will be equal to 5. Let us take one more example. 2897. So the digital sum in this case will be 10, 19 plus 7, which will be 26. Now 26 is not divisible by 3. So we can say that this number is not divisible by 3. What will be the remainder? It will be same as 26 divided by 3. 26 divided by 3, the remainder is 2. So the remainder when this number is divided by 3 will be equal to 2. Likewise for 9, 26 is not divisible by 9. Hence this number is also not divisible by 9. What will be the remainder? It will be same as when 26 is divided by 9, which is 8. So the remainder when this entire number is divided by 9 will be also equal to 8. By extending the same divisibility rule of 3 and 9, we can determine whether any number is divisible by a number which is of the form of 10 raised to n minus 1 or not. If not, then what is the remainder? Let us consider an example. 4950. So if you want to check what is the remainder or whether this number is divisible by 9 or not, what we were doing was we are taking the digital sum by considering one digit at a time, because 9 is equal to 10 raised to 1 minus 1. Hence we are taking only one digit at a time for taking the digital sum. So that was 0 plus 5, 5 plus 9, which was 14, 14 plus 4, which was coming out to be 18. So 18 was divisible by 9, hence we can say that this number is divisible by 9. But in case of 99, which is of the form of 10 square minus 1. We will take the digital sum by considering 2 digits at a time. So for this example 4950, the digital sum will be 50 plus 49. So 50 plus 49 will give us 99. Since this digital sum is divisible by 99, we can say that this entire number is divisible by 99 as well. Likewise for 999, which is of the form of 10 cube minus 1, we will take the digital sum by considering 3 digits at a time. Let us take one example. Suppose if you want to find whether this number 3, 4, 5 up till 300 terms is divisible by 999 or not. If not, then what is the remainder? So how we will do this? Now since 999 is 10 cube minus 1, we will take the digital sum by considering 3 digits at a time starting from the right hand side. So since there are 345, 345, 300 terms, if you see this 345, 345, they are repeating in groups and there are 300 terms. That means there are 100 groups of 345. So what will be their sum? It will be nothing but 345 into 100. So the digital sum will be 34500. Now if we divide this number by 999, then we'll get our answer whether this number is divisible by 999 or not. If not, we'll get our remainder also. So how do we divide this number by 999? Consider this. 1000 when divided by 999, the remainder is 1. When 2000 is divided by 999, the remainder will be 2. When 3000 is divided by 999, you will find that the remainder is 3. So if you observe the pattern, if n,000 is divided by 999, the remainder will be equal to n. So in this case, we have 34,500. So we'll split this up into 34,000 plus 500 and we'll divide this by 999. So 34,000 when divided by 999 will give us a remainder of 34, and 500 when divided by 999 will give a remainder of 500. Since 500 is less than 999, it is not divisible by 999. So the remainder will be 534. Hence the remainder of this entire term when it is divided by 999 will be 534. In the similar way, you can find the remainder when the number is divided by 99999, 4 times 9, and so on. You can also check for divisibility. Let us now understand the divisibility rule of 11. In this case, we will find the sum of all odd place digits, and from this we will subtract sum of all even place digits. If this difference comes out to be 0 or 11, then we can say that the number is divisible by 11. If it comes out to be some other number, then that will represent the remainder when that number is divided by 11. Let us consider an example, 1129. In this, 9 is at the first place, which is an odd place. The number 1, which is at third place, it is also an odd place. Number 2, which is at the second place, which is an even place, and this one, which is at fourth place, is also an even place. So if we take their sum, 9 plus 1, and subtract from it the sum of even place digit, which is 2 plus 1, we'll get 10 minus 3. The answer comes out to be 7. Since it is neither 0 nor 11, we can say that this number 1129 is not divisible by 11. So the remainder in that case will be equal to 7. Remember, you have to start counting from the right hand side. You cannot count from this side. Okay, it will give you a wrong answer. If we take another example, let's say 2156. If we take the sum of all the odd place digits and subtract from it the sum of all even place digits, it will be 6 plus 1 minus 5 plus 2, which is 7 minus 7, which is coming out to be 0. Hence we can say that this number is divisible by 11. So in this way you can find the remainder when a number is divided by 11, or you can check for divisibility by 11. We can extend the same logic for checking whether a number is divisible by a number which is of the form of 10 raised to n plus 1 or not. If not, then we can find the remainder. Like in the case of 11, we are finding the difference between sum of odd place digit and sum of even place digit. In the case of 11, 101, 1001, 10,001, we will also find the difference between sum of odd place digit and even place digit. But in case of 11, which was of the form of 10 raised to 1 plus 1, we were taking one digit at a time. In case of 101, which is of the form of 10 square plus 1, we will take 2 digits at a time. Similarly, in case of 1001, which is of the form of 10 cube plus 1, we will take 3 digits at a time, and so on and so forth. So let us take an example and understand this concept. Let us take this number 909787. So if you want to check what is the remainder when this number is divided by 101, or if you want to check whether this number is divisible by 101 or not, we'll take the sum of all odd place digits, and from that we'll subtract the sum of all even place digits. 101, which is of the form of 10 square plus 1, we'll take 2 digits at a time. So 87 plus 90, which will give us 177. From this we'll subtract the sum of even place digit. There is only one number, which is 97. If we subtract 97 from 177, we are going to get 80. Now since 80 is not divisible by 101, hence we can say that this entire number is not divisible by 101. What is the remainder? The remainder itself is 80. Let us take one more example. 208767. We'll find the sum of all odd place digit and even place digit. So it will be 67 plus 20, which will give us 87. From this we'll subtract sum of all even place digits, which is 87. So 87 minus 87, which comes out to be 0. Hence we can say that this number is divisible by 101. So for 1001, which is of the form of 10 cube plus 1, we'll take 3 digits at a time for finding the sum. Likewise, we can proceed for higher numbers as well. Let us now understand the divisibility rule for 7. In this case, we will try to reduce the number. Let's see how it is to be done. Let us consider this example 4802. If we want to check whether this number is divisible by 7 or not, then we'll take the last digit, we will double it and subtract it from the rest of the number. So in this case, the last digit is 2, double of it will be 4. We'll subtract 4 from 480. So this will give us 476. Now still it is not clear whether this number is divisible by 7 or not. So we'll again repeat the same procedure. We'll take the last digit and subtract it from the rest of the number. So double of it will be 12. 47 minus 12 will be 35. Now clearly 35 is divisible by 7. Hence we can say that this entire number is divisible by 7. Let us take another example. 24597. So to check whether this number is divisible by 7 or not, we'll first take the last digit, double it, subtract it from the rest of the number, which will be 2459 minus 14, which will give us 2445. Again, it is not clear. We'll double it and subtract it from the rest of the number. So this will give us 234. Still it is not clear. We'll again repeat the same procedure. So 23 minus 8 will give us 15. Now 15 is clearly not divisible by 7. Hence we can say that this entire number is not divisible by 7. Let us now understand how to check for divisibility by a composite number. So if we consider for an example a number which is 189450. If we want to check whether this number is divisible say by 24, 15, 36. So first thing that we have to do is we'll have to represent this divisor, which is a composite number, as a product of two co-prime numbers. So 24 can be represented as a product of 3 and 8. Since the HCF of 3 and 8 are 1, we can say that these numbers are co-prime. Likewise, 15 can be represented as 3 into 5, again a product of two co-prime numbers. 36 can be represented as 9 into 4, again a product of two co-prime numbers. Now we'll check the divisibility of this number by each of the co-prime numbers. If this number is divisible by each of these co-prime numbers, we can say that this number is divisible by the original number. But if it is not divisible by any one of these numbers also, then we can conclude that this number is not divisible by original number. So let us check for 24 first. So 24 is 3 and 8. So we'll check for divisibility of this number by 3. For that we'll have to take the digital sum, which will be 9 plus 9 18, 18 plus 9 27. So 27, as we know, is divisible by 3. So this is okay. For 8, which is of the form of 2 cube, we'll take the last 3 digits and check. Since 450 when divided by 8, the remainder is coming out to be 2. Since 450 is not divisible by 8, we can say that this number is not divisible by 24. Let us check for divisibility of this number by 15. Since 15 is written as 3 into 5, as we have already seen that the digital sum of this number is divisible by 3, so it is fine. For 5 we have to check the last digit. Since last digit is 0, which is divisible by 5, we can say that this number is divisible by 5. Hence we can conclude that this number is divisible by 15 as well. Likewise, if you want to check the divisibility by 36, which is 9 into 4, for 9 we'll have to find the digital sum, which was 27. Now since 27 is divisible by 9, so this is okay. For divisibility by 4, we'll have to check the last 2 digits. So last 2 digits in this case are 50. So 50 is not divisible by 4. The remainder is coming out to be 2. Hence we can say that this number is not divisible by 36. Let us now understand the concept of remainder theorem. In this, we will first understand what is positive remainder and what is negative remainder. If we take, let's say, a number 23. So 23 when divided by 12, the remainder, as we know, will come out to be 11. This value of remainder is positive, hence it is called as positive remainder. Another way to find the remainder is 23 when divided by 12. As we know, 12 into 2 is 24. But the original number that we are dividing is 1 less than 24. So the remainder in this case will be minus 1. This is called negative remainder. But remainder can never be negative. So to make it positive, what we will do is we will add the divisor to it. So the divisor in this case is 12. So add 12 to it. We will get the remainder, which is 11. So remainder is always expressed in positive term. But negative remainder will help you in calculations. Let us see how. Let us consider this example. 34 into 96. If you want to find the remainder when this number is divided by 14. So one way of doing it is first find the product of these two numbers and then divided by 14, which is quite a lengthy one. What we'll do instead is we'll find the remainder when each of these numbers are individually divided by 14. So 34 when divided by 14 will give us a remainder of 6. Whereas 96 when divided by 14 will give us a remainder of 12. So now we'll take the product of these two numbers and find the remainder when this number is divided by 14. So this will be 72 by 14. 72 when divided by 14, the remainder is 2. Hence the remainder when this original number 34 into 96 divided by 14, the remainder will be 2. So instead of multiplying them and then finding the remainder, we can find the individual remainders, then multiply them, simplify it further and find the remainder. So this was by using positive remainder. We can use negative remainders as well. Let us consider the same example. 34 into 96 divided by 14. So 14 into 3, as we know, will come out to be 42. So the negative remainder when 34 is divided by 42 will be minus 8. Likewise, in case of 96, the negative remainder will be 14 into 7, as we know, will be 98. So the negative remainder will be minus 2. So we'll have to take the product of these two and find the remainder when it is divided by 14, which will be this minus and minus will become plus. 8 into 2 will become 16. 16 when divided by 14 will give us a remainder of 2, which is the same answer that we are getting. Not just that, you can use the combination of positive and negative remainder as well. Let us see how. We'll take the same example, 34 into 96 by 14. So in the first case, we'll take the positive remainder. In the second case, we'll take the negative remainder. So positive remainder when 34 was divided by 14 was 6. And the negative remainder when 96 is divided by 14 was minus 2. So we'll take the product and divide it by 14, which will be minus 12 divided by 14. So minus 12 divided by 14 will give us a remainder of minus 12. As I have said previously, remainder can never be negative. We'll have to make it positive by adding the divisor. So we'll add 14 to it. So we'll get the remainder as 2, which is again the same answer. So in this way, you can use positive remainder and negative remainder to arrive at your answers. Let us see now how different types of problems can be solved using the remainder theorem. Let us consider this expression, 21 into 23 into 27 into 64 into 72 into 46 into 15. If you want to find the remainder when this entire number is divided by 75. So how we are going to do that? We are going to find the remainder when these numbers are individually divided by the divisor. But as you can see in this case, these numbers are very far away from the divisor. So by taking the individual remainder, it will not help us. So what we will do is we will reduce this number first. So as you can see, 15 ones are and 15 fives are is 75. So what we will do is we will instead find the remainder when this number is divided by 5, and when we get the remainder, we will multiply that number by 15, because we have divided it by 15, hence we'll have to multiply it by 15. Remember that. It is very important step, don't forget that. So the remainder when 21 is divided by 5 is 1, 23 by 5 will be 3, again 2, then 64 by 5 will give us a remainder of minus 1. We are using a negative remainder here. 72 by 5 will again give a negative remainder of minus 3. 46 by 5 will give a remainder of 1. So this whole thing we'll have to take and then divide it by 5. So if we multiply all these numbers, we'll get 3 into 2 will be 6. 6 into 3 will be 18. And this minus and minus will cancel out. So we'll get 18 upon 5. So 18 when divided by 5 will give us a remainder of 3. Now we'll have to multiply this 3 by 15. So we will get 45. So the remainder when this number is divided by 75 will be equal to 45. Let us consider now another type of an expression. Suppose if you want to find a remainder when a number is of the form of n raised to a upon d. Let us take an example. Let's say 81 raised to 600. You want to find the remainder when this number is divided by 7. So what we will do? First, forget the power. We don't need to consider the power. Just simply divide the base and find the remainder. So 81 when divided by 7 will give a remainder of 4. Now 4 raised to 600 by 7. We'll have to find the remainder when 4 raised to 600 is divided by 7. As we know, 4 cube is 64. And 64 when divided by 7 will give a remainder of 1. So we will try to write this number in the form of 4 cube. So we can write this number as 4 cube the whole raised to 200. Since 3 into 200 will give us 600 divided by 7. 4 cube was 64 upon 7. Now 64 when divided by 7 give a remainder of 1. 1 raised to 200, which will be 1 by 7, which will give a remainder of 1. So this number, 81 raised to 600 when divided by 7 will give a remainder of 1. So in this way you can simplify the numbers step by step and arrive at your answer of remainder. There is another method by which you can find the remainder of such high powers by using the cyclicity principle. Let us see how. Suppose if you want to find the remainder when the number 32 raised to 32 is divided by 7. So again, our first step will remain the same. We'll forget the power, we'll divide the base and find the remainder. So in this case, we'll get 4 raised to 32 by 7, because 32 when divided by 7 will give us a remainder of 4. Now, 4 raised to 1 when divided by 7, the remainder will be 4. 4 square when divided by 7, which is 16 by 7, the remainder will be 2. 4 cube when divided by 7, which is 64 by 7, the remainder will be 1. 4 raised to 4, which is 256. 256 when divided by 7, the remainder will come out to be 4. And in this way, the values will start to keep on repeating. We'll get for 4 raised to 5 when divided by 7, the remainder will come out to be 2. Then for 4 raised to 6 by 7, the remainder will come out to be 1. And then again 4 to 1, 4 to 1. So it will keep on repeating. If you observe, the values are repeating in a set of 3 numbers. So the cyclicity of 4 when divided by 7 is 3. We will express this power in the form of 3k plus n, where the value of n can be 0, 1 or 2. If the value of n is 2, if the value of n comes out to be 2, we'll check the remainder for 4 raised to 2. If the value of n comes out to be 1, we'll check the remainder of 4 raised to 1 by 7. So it will be 4. If the value of n is 0, that means the cycle is completing. We have no extra value. Hence, we will check the remainder for 4 raised to 3 divided by 7. So in this case, we can represent 32 as 3 into 10 plus 2. So the value of n is 2. So in this case, the remainder will be 2. Another method for solving this type of problem is by using the Euler's torsion method. So what is Euler's torsion? A number which is of the form of m raised to Euler's torsion of n when divided by n, the remainder will be equal to 1. So first of all, understand what is an Euler's torsion. It represents the number of numbers which are less than it and co-prime with it, and it is given by m into 1 minus 1 by x into 1 minus 1 by y into 1 minus 1 by z, where x, y and z are the prime factors of that number. Let us understand it with the help of an example. If you want to find the Euler's torsion of 15, so 15 can be represented as 3 into 5. So as I have said, Euler's torsion represents the number of numbers which are less than 15 and co-prime with it. If we list it down manually, it will be 1, 2, then 4, the next number will be 7, 8, then 11, 13 and 14. So these are the numbers which are less than 15 and co-prime with it. If you count it, it will be 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 numbers which are less than 15 and co-prime with it. This was by manual calculation. If the number is large, you cannot list them down and count it. You can use directly this formula and find what is the Euler's torsion. So this will, in this case of 15, it will be given by 15 into 1 minus 1 by 3 into 1 minus 1 by 5, where 3 and 5 are the prime factors of this number. So the Euler's torsion will be given by 15 into 2 by 3 into 1 minus 1 by 5 will be 4 by 5. So 3 into 5 is 15, 15 and cancel out, we'll get 8. So it is the same answer that we have got by manual calculation. So if we are able to represent a number in the form of m raised to Euler's torsion of n, where n is the divisor and m and n are co-prime numbers, then in that case remainder will be equal to 1. So let us take an example and solve it by using this method. So if you want to find the remainder when 7 raised to 50 is divided by 90. As you can see, 7 and 90 are co-prime numbers. So first we will find what is the Euler's torsion of 90. So 90 can be written as 9 into 10, which is 3 square into 2 raised to 1 into 5 raised to 1. So the prime factors of 90 are 3, 2 and 5. So the Euler's torsion will be given by 90 into 1 minus 1 by 2 into 1 minus 1 by 3 into 1 minus 1 by 5. Remember, we are not taking 3 square, we are just considering the prime factor. We are not taking the entire number. So we will just consider 3 here. So this will be 90 into half, 1 minus 1 by 3 is 2 by 3, and this will be 4 by 5. So 2 into 3 is 6, 6 5 is 30. So this will give us 30 into 3, which will be 90. So 3 into 2 is 6, 6 4s are 24. So the Euler's torsion of 90 is 24. Hence, we will split the numerator in the form of 7 raised to 24. So this will give us 7 raised to 24, the whole square. So 24 into 2 is 48. We still have 2 7s extra. So we will represent it separately, 7 square. And this entire thing is divided by 90. So the remainder when 7 raised to 24 is divided by 90 will be equal to 1 by using the above concept. So this remainder will be 1. We will have 7 square upon 90, which will give us 49 upon 90. So the remainder when 49 is divided by 90 will be 49 itself, because it is less than 90. Hence the remainder when this number is divided by 90 will be equal to 49. Let us now understand two other important concepts, that is Fermat's theorem. As per Fermat's theorem, a number which is of the form of a raised to p minus 1 upon p, where p is a prime number and a is not a multiple of p. If a number is of this form, the remainder in that case will be equal to 1. So if we take an example, let's say 5 raised to 12 when divided by 13. Since 13 is a prime number and this is 13 minus 1 and 5 is not a multiple of 13, we can say that the remainder in this case will be equal to 1. Another form of this theorem is a raised to p upon p, where p is a prime number and a is not a multiple of p. So in this case, the remainder will be equal to a. The example of this type will be, let's say 7 raised to 17 divided by 7, where 17 is a prime number and 7 is not a multiple of p, so the remainder in this case will come out to be 7. The last concept in this lecture and the most important one is the Wilson theorem. As per Wilson theorem, a number n minus 1 factorial when divided by n, where if n is a prime number, the remainder will be equal to n minus 1. If n is a composite number, then the remainder will be equal to 0. Another form in which this formula can be used is n minus 2 factorial when divided by n, where n is a prime number, the remainder will be equal to 1. Let us see how we can use this concept to arrive at our answers. So if you want to find the remainder when 95 factorial is divided by 97. So 95 factorial is nothing but 97 minus 2 factorial. And since 97 is a prime number, we can say that the remainder in this case will be equal to 1. Suppose if you want to find the remainder when 93 factorial is divided by 97. Now this is not a direct application of the Wilson theorem, but we can still apply it. We know that n minus 2 factorial, when divided by n, the remainder is equal to 1. But in this case, we have to find 93 factorial by 97, which is n minus 4. So first of all, let's assume that the remainder in this case will be equal to r. Now we know that 95 factorial upon 97, the remainder will be equal to 1. We can write this as 95 into 94 into 93 factorial divided by 97. The remainder in this case is 1. So 95 when divided by 97, the remainder will be minus 2. 94 when divided by 97 will be minus 3. And 93 when divided by 97, we have assumed the remainder as to be r. So this will be equal to r. And this whole thing when divided by 97 will give us a remainder of 1. We can simplify this thing. So this will become 6r when divided by 97 is giving us a remainder of 1. So this is the dividend, this is the divisor, and this is your remainder. So we can write this as 6r, which is the dividend, as equal to divisor into some quotient plus remainder. So the divisor in this case is 97, quotient let's assume it to be k, plus the remainder, which is 1. So by solving this expression, we can find our value of the remainder r. So how we are going to solve this? As you can notice, the left hand side is a multiple of 6. So the right hand side should also be a multiple of 6. That means 97k plus 1 should be a multiple of 6. So you will have to find such a value of k so that it becomes a multiple of 6. So by substituting k is equal to 1, 2, 3, you can do that. But the simpler way of doing this will be, we will divide this right hand side by 6. So on the left hand side we will get r is equal to 97k plus 1 divided by 6. We can split this 97 as 96k plus k plus 1 the whole divided by 6. Now as we know, 96 is divisible by 6. So this part will be divisible by 6. Hence this part should also be divisible by 6. So the smallest value of k for which this part will also be divisible by 6 will be k is equal to 5. So now we'll substitute this value of k in this equation and we can get our remainder. So the remainder will be 96 into 5 plus k, which is 5 plus 1 the whole divided by 6. So this we can write it as 96 into 5 by 6 plus 6 by 6. 6 ones are 6, 16s are. 16 into 5 will be 80 and 6 by 6 is 1. So the remainder will be 81. So the remainder when 93 factorial is divided by 97 will be equal to 81. So in this way, by using the Wilson theorem and a slight modified format of that, we can find the remainder. So this is all about this lecture. Thank you.